Welcome back to the GMMDC YouTube channel. This is a video on the topic statistics and grade 12 topic regression, correlation, and the line of best fit. So in this video, we're going to look at a statistics topic that is actually grade 12 mathematics CAPS, and it is on the least square regression line, or also known as the line of best fit. In this video, we're going to first of all look at the introduction to the concepts of correlation and regression, and then we're going to look at the application using scatter plot, and then looking at the line of best fit and looking at more details on correlation. Thereafter, we're going to show you how you can calculate the equation of the line of best fit, and there are two ways: using a formula that's provided or using the stat mode on your calculator. Then we're going to have some applications with regard to trends, outliers, prediction, and correlation coefficient. And then we're going to have a general application of all the above concepts. And as usual with all my videos, there's going to be an exercise worksheet for you based on questions from external examination papers. Hope you will enjoy it. So let's introduce you to correlation and regression. What are we going to do with this section on statistics? We're going to study the relationship between two variables, and we're going to use a statistical method or a statistical technique known as regression, right? For example, if we want to study the relationship between hours that you study, how many hours you put into study, and what your examination results would be based on your hours. So we're going to study an example like that, okay? And what we're going to do further is we're going to develop a model, right, of this relating to this relationship, and then we're going to use this model to make some predictions. So for example, we've got the example of examination times that you study and your examination result. So we're going to say, if you know how many hours you study, maybe we can predict what your exam result would be. And that is what we're going to do, and we're going to have many examples to illustrate this to you. Now, what do we mean when we talk about regression, and specifically linear regression? Linear regression is a statistical technique to find out exactly which linear function best fit or suits the set of given data. So if you have a given data, you want to find a linear function that would best fit that set of data. Okay. Now, regression also means that we want to understand how the value of the dependent variable change with respect to an independent variable. So we've got two things: a dependent variable and an independent variable. When we have observed data, in other words, data that you determine, that involves two variables, right? So when we have data that involves two variables, we refer to it as a bivariate data. And this bivariate data, then, because we say two variables, one of the variables is known as the dependent variable, and the other one is referred to as the independent variable, right, as we mentioned previously. Now, the dependent variable is actually the variable we want to predict. This is the one we want to predict. And the independent variable is the variable that we use to make that prediction. Now, for the dependent variable, we will use the symbol Y to represent the dependent, and the independent variable will represented by an X, right? So, for example, we would say that the examination results, that's the thing we want to predict, will be your dependent one, and the independent one is the hours that you studied. Now, what is meant by a simple linear regression? Let's look at the three words, right? Simple means that there is only one dependent and one independent quantitative variable. Okay, linear, that means that the relationship is approximated, or the relationship is modeled using a straight line, linear straight line. Then what do we mean by regression? Regression is the statistical technique of finding a linear function that best fit or best suits the data set. Now let's look at the simple linear regression equation that we will use, right? Now it's important here that this equation is based on a sample of bivariate data, not the population data that we have, just the sample, right? And the formula here, we have the formula. Now we've got a little symbol there. And how do we read that symbol? We read that as y hat, right? So that little symbol is read as y hat equal to a plus bx. Okay. Now, what does the y hat stand for? The y hat is the predicted value of y given for a given x value. So that's the predicted value for a given x value. And what do we mean by the a? The a, as we know from the linear equation, a would represent the y-intercept. Normally we have the formula mx plus c, right, where m is the gradient and c is the y-intercept. Here we just write it the other way around. We first put the y-intercept down first. That's what is normally done in statistics. It doesn't matter, you can write it the other way around. So a represents the y-intercept of the line, and b, then what would b represent? B is like the m. That's right, b represents the slope or the gradient of the line, right? So it's very similar to our normal linear function equation, y equal to mx plus c, but in statistics we don't use m and c, we normally use a and b. And those are the two symbols that's actually available on the formula sheet as well. Small a, lowercase a, and lowercase p. Next, we're going to look at the graphical representation called a scatter plot. And then we're going to show you what we mean by a line of best fit, just to illustrate that to you using the scatter plot. And then we're going to just expand a little bit about the terminology which you refer to as correlation. Now, the scatter plot is a way of representing a data set. And it's important here that we're only going to work with sample data, not population data. So there we've got a sample of data, so it's a small set there. And just to make it easier for us here, later we'll actually use more realistic values. I've just taken the numbers 1, 2, 3, 4, 5, 6, and 7 for the one variable. Which variable is that? That's the independent variable. And then we have some values here for the dependent variable, right? I've chosen those numbers to make the calculations a little bit easier. So what do we need to do? We need a dependent and an independent variable. But the variable we put on the horizontal axis here, that is the independent variable goes there, right? So for example, if the x represents the number of hours studied, so this is the independent variable. Then we have, we can color code it as well. The other one here is on the vertical axis, and there we always put the dependent variable. In this case, it's we want to find the relationship between number of hours and examination result there. And then we have, because if we look at there, the x values goes from 1 to 7, so we need to have a scale that we can use. You can see there's from 1 to 7, we just extend it a little bit. And here I have, you can see what is the maximum value here, 93. So let's go up to 100. Okay, so there we have the number of hours studied, and that is the examination result there. Now what do we need to do? We need to plot that. So there I have 1 and 49. X is 1 and y is 49. So let's look at that. There's that point. I plotted that, you can see there, 1 and 49. And I plot the other one there, that's at 2 and 59. There's 2 and 59, and I plot the other one, 3 and 71. You see, we just plotted carefully there. And then 4 and 67, you just get it approximately there. and then we have 5 and 77. There's 5 and 77, and then we have 6 and 74, and then we have 7 and 93. So you just have to plot those points there. So you can see those points there, they're all not in a straight line, they're sort of scattered or dispersed there. So there we can, that's why we refer to this as a scatter plot. Right? So be careful that you always put the independent on the x and the dependent on the y. So that's the x and the y values there. And there we've got our scatter plot. Now, if we look at the scatter plot, we'll notice here that as the x values increase, the y values increase, right? You can see there, 1 went with 50, 2 went with a larger number, 3 went with a large. So, and in this case here, you can see this line, if you just look at that relationship, as the x increase and the y is also increase, then we refer to this as a positive linear relationship, right? X increase, y increase, that's a positive relationship there. So next what we're going to do is, if you have a scatter plot, we want to draw the line that best fits that data, right? You can see that you can have a line like that. You're going to see how you can actually, what's the best way of getting that particular line. So what we need first of all, we need to have the mean of your variables. So if I find the mean, so it's the sum of the values divided by the number. So if I say 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, if we add that up, it's 28 divided by 7, and I get 4. Right? So in other words, let's just have that mean. So let's represent the mean. There's the mean for the independent variable. Right? Then we want to find the mean for the dependent variable. That's 49 plus 59 plus 71 plus 67 plus 77 plus 74 plus 93, which gives me 490. And I divide it by 7. That's right, the answer is 70. So there we have the mean. Now the line, the best fit line will always go through the point of intersection of these two means there. So in other words, the best fit line should go through there. Okay. Now let's just draw a line here. So if you draw a line, you can see there are many lines that will go through that point. So if I take this line, we always try to draw the line so that you can see this line, above the line we've got 3 points, and below the line we've got 3 points, and one of the points is near. So this line is not so bad. We always try to have the number of data points above should be the same as the number of data points below. So in this case, that doesn't seem to be such a bad fit there. But somebody else could have taken this line. If you look at this line here, we can see there we've got 2 points on the line, which is maybe a bit better than the previous one. Previous one only had 1 point close, and we've got 2 on it. So maybe this orange one here is maybe a better fit than that magenta one. Let's try another one. Let's look at this one here. If I look at this one there, so there I also have 2 points above and here, but here I've got more points. So maybe this red one is not such a good fit, right? So when you have to draw something by hand, there are many options that can be regarded as correct. But it's essential that you draw it always through the point of intersection of the two means. If it doesn't go through there, that will not be a good representation of the line of best fit. And this particular line of best fit, we also, as we said, we can also recall it the regression line. So there we've got 3 possible options for the regression line there. Okay, and this is not unique, you know, mainly because you're using your eye to count it. What if there's a lot more points? It might be a little bit more difficult. Later we'll show you a more accurate way of getting that line of best fit. Now let's look at the term correlation, right? The relationship between two quantitative variables, that relationship, instead of just talking about the relationship of the two variables, we can say it's a correlation. So correlation is actually just one word to explain the relationship between two quantitative variables. Okay, let's look at the word correlation. It has a prefix which is co, which means co, together, and then relation means a connection. So this is the together connection, or the connection together, the connection between the two variables. Let's look a little bit further about correlation. Now, the important is we want to look at now, if we have a data set, we want to see, is there a relationship between variables? Maybe there is a relationship, maybe there's not a relationship. So this is what we want to determine. This is our statistical technique we'll use to determine if there is a relationship between variables. Okay, so let's look at this particular example here. Here we have the income in monthly income in thousands of rand, and then we have on the dependent one the amount that you save. You can see there. So there we've got the scatter plot, and we see this scatter plot there. It forms a linear pattern. If I can draw a line. So this will be a linear regression. And this particular one here, we can see as the monthly income increase, then the amount saved also increase. So this particular relationship here, as the X increase and the Y increase, we refer as this is a positive. There is a relationship, and that is a positive relationship there. Okay, and we refer to this as a positive correlation. Remember, instead of saying relationship, you can also say correlation. Let's look at another example here. Let's look at this one. In this case here, I have the age and the expenditure. So it seems that if you look at this, as people get older, they seem to spend. That's right, they seem to spend less. So as the one increase, the dependent one decreases. So this type of relationship, you can see it goes in this direction there. That's correct. That is as X increase and Y decreases, that gives us a negative relationship. Instead of saying negative relationship, we can say it's a negative correlation. Okay. Now let's look at another one here. Let's look at this scatter plot there. Is that positive or is it negative? It's not possible to determine. So we do get relationships here where we cannot determine whether it is positive or negative. Then we say there's no relationship. And in this case here, we refer to it as a zero correlation. Okay. Now we need a measure, and the measure of correlation is known as the correlation coefficient. Okay. So the correlation coefficient is actually the measuring the strength of the relationship, right? And we use the letter R. So, and a correlation coefficient is a single value that lies between -1 and 1, with the -1 included and the positive one included. So it's not just between, it's from -1 to 1. Now we can actually represent it mathematically. So R there lies between -1 and 1, with both the -1 and the 1 included. Right? So that is the measurement, that's the R value there. Where if it's positive, if it is just +1, exactly +1, we refer to it as a perfect positive relationship. That's the perfect one. Or if I get a -1, that means it's a perfect negative relationship. And the one right in the middle, which one is that? That is the 0. That's correct. That means there's no relationship. Okay. We're going to look at it in another way in the following slides. What does the correlation coefficient tell us about our data set? Okay. First of all, it fits a straight line to the data. Okay. And it also indicates the direction of the slope or the direction of the gradient. So the correlation will tell us whether it is positive or whether it is negative. And then the correlation will give us the strength of the first, right? Or the size or the measurement, right? And remember, that can be any value between -1 to +1. Now, a correlation coefficient, as we said, it's the fit of the line to the data. How does the line fit to the data? If I look at that data set there, right? We're taking a very easy one, just with 4 points, so it's much easier to. So if I want to have a line there that can represent it, let's just put a line in by hand here first, right? So let's say this particular example, where the independent is the duration or the time of a TV show. So there we have different TV shows stretching from 10 minutes up to 110 minutes. And then we're going to relate it to the star rating, right? And we have normally a 5-star rating. And you can see the 60-minute video from this has a 1-star rating, and the 70 has a 3-star, and the 90-minute has a 2-star there. So we can see this here. There's some relationship here. And what type of relation do you see this? That's right. It forms a positive relationship, or it's a positive correlation. So let's represent that, the data there. So in this case here, there we've tried to fit a line to the date. I could have put the line somewhere else, but let's just do it by hand. So it is with just an approximate position for that line. Let's look at the direction of the line. So if I take that same example, there's my data set with a line of best fit that I've just drawn in by hand, and we can see this direction here. It's going in the positive direction. So this is a positive positive slope or a positive correlation. As you can see, as the time of the TV show increases, it seems that the rating increases there. And here, because it's positive, the R value will be somewhere between 0 and 1, right? Why don't I have an equal there? It's not, there is a relationship, so I don't put the equal there. And it's not a perfect relationship, right? The correlation is not, because you can see these points don't lie on that line. It's a little bit far away from it, right? It's not the best line. The data set there, we don't have a perfect correlation there. We're going to look at the strength of the correlation coefficient. What is the strength of the fit to the data set there? Now, the correlation coefficient is a value between -1 and 1. So it's a value between -1 and 1. So that is the perfect one, and that's a perfect positive, and that's a perfect negative, and this one has no correlation there. Okay. Now, the closer you are to 1, the stronger it is. So this is if we can see where my pointer is there, it's very close to 1, so it's a strong positive. It's very close to the -1, so it's a strong negative, right? If it's very close to the 0 again, it's going to be a weak positive. If it's on this side there, it's a weak negative. So we have a range between -1 and 1. So let's just have that there. So you can see it's somewhere between -1 and 1. Let's look at the different cases there. When it's 0, you can look at the scatter plot. You see there's no relationship, so that's definitely no relationship. So we have the measure there is R is equal to 0. And in this case here, you can see those points perfectly fit a straight line there. So this is a perfect arrow, and then it's exactly 1. This one here also is a perfect fit. All the points lie on the line. And this is a perfect negative correlation. Now let's look at the different values here. If I look at this one, you see there's a scatter. And this scatter there is a little bit better than this, a lot better than the 0. So this one here is approximately, let's say, 0,4. Okay. And on the negative side, you can see there's a negative correlation. The points are scattered there. If you have a line, there are many points that are away from the line or not on the line. If you go a little bit closer to the 1, you see those points there, they seem to cluster together on that straight line. So it has a higher correlation value there. That's 0,7. And on this side there, we've got a negative correlation, and you can see it's getting closer to the perfect correlation there. The points are much closer to the line of best fit. So there we have the different ways you can have. So that's perfect. This is still positive, but it will maybe say it is a strong positive. Okay. and maybe this one here is going to be a weak positive. That is a strong negative, and this is a weak negative there. Let's look at it another way as well. So we know it's the measurement between -1 and 1. So let's look at it this way now. First of all, we've got the 0, right? So that's the 0. R is 0. There's no correlation. R is 0. Then we have the two extremes there. So on the right side of 0, what do we get on the right side of 0? We have got the positives. And on the left side of 0, we've got the negatives, right? So if I look at the positive there, that's how we can write that. R exactly equal to -1, R exactly equal to 1. Positive R greater than 0 is positive, and R less than 0 is negative. That's just the mathematical notation for that word negative and positive. Now, if we look at that one, that is the perfect positive correlation, and that one is the perfect negative correlation. Now let's look at the different ones we can have there. The one that's very close to the +1, we get 2. That is a strong one. But maybe you can take it, if it's more than 0,8, you'll maybe say it's a very strong one. And if it's somewhere between 0,6 and 0,8, then we just say strong. If it's more, then we say very strong. And if it is in the same year on this side here, this is a very strong negative one. And this is a strong negative one. That's a very strong positive. I've color coded it there. The yellow represents negative and the green represents positive. Then we have weak. Can you see this weak one here is very close to the 0. So if R is less than 0,4 or R is greater than -0,4, that will be weak correlation. And then we've got the one in between the 0,4 and the 0,6. We refer to that as a moderate, right? So that's moderate, somewhere between 0,4 and 0,6. That's a moderate positive, and the same way we get a moderate negative there. Okay, so you can also look at it that way. So this is a terminology. You have a 0, you have a perfect, you have a very strong, and you have a strong, and you have a moderate, and you have a weak. In this section here, we're going to show you how to find the equation of the line of best fit. And there are two ways of doing it. One, using a formula which is provided to you on a formula sheet, or you can make use of your calculator using the stat mode on the calculator. Now, in this section here, we're going to show you how to find the equation of the line of best fit. And here we're going to make use of formulae that are provided to you, right? That's our data set, and that is the mean for the independent, and that will be the mean for the dependent. The predicted value has that formula y hat equal to a plus bx, where a stands for the, that's correct, the y-intercept, and b stands for the gradient or the slope, right? And the formula for the slope is given. There's the formula of the slope. And you can see there we want to have, what does the sigma mean? That's correct, the sigma means sum. So we want to determine the sum. And what does this symbol mean here? That is the mean for the x values, and that's the mean for the y values. We have to find a difference there, and find a difference and a product, and the sum of those products. And then here we want to find a difference, and we want to square it, and then the sum of the square. So we're going to go through that whole process. And to find the y-intercept, we just make the y-intercept is the a. If we make a the subject, we obtain b times the mean for the x values minus the mean for the y value. So these formulas are provided to you. You don't have to memorize them. So let's go to our, let's try to calculate now for this particular data set. That will do on the next slide. I'll show you how we can find the line of best fit for that data set there. So there's our data set, and that is the formula that we're going to use. That's the predicted value, and then the formula for the b, and we can get the formula for the a. So these are the formula we're going to use. Now we just need that space. Let's just put it somewhere on the left side there. Let's take it away and just let's put it down there in the meantime, right? So what do we need? We need the mean for the independent, the mean for the x values, and the mean for the y values. So we have to calculate the difference between the x and the x values, corresponding x value, and the mean there. So we need to get the mean, and the mean there is 4, right? So what do we need to do? It's the x value minus the mean. So it's the 1 minus the 4. So let's see that. So we take the 1. See, there's the 1 there. And we're going to subtract from it the mean. And what is 1 minus 4? Easy. I'm taking very cosmetic numbers, which is easy to calculate. That gives me negative 3. The same way for the next one. What will it be? That's correct. It's 2. The 2 minus the 4. The 2 minus the 4. And what is 2 minus 4? That's correct. It is negative 2. Right? And we can do the same with the other. So that's 3 minus 4. 4 minus 4. 5 minus 4. 6 minus 4. And if we do all those calculations, those are the values that we're going to obtain there. Okay. Then, so that we worked out that particular portion there. Then we need to find the same with the y values, right? So we have the column there. So that's y minus the mean for the y's. And we need to find the mean for the y. We worked it out previously. That is 70. So now this will be 49 minus 70. So there is it. 49 minus 70, easy arithmetic. That gives you, that's correct, negative 21. Okay, and we can do the same now. 59 minus 70, 71 minus 70, 67, etc. So if we fill in all those values, those are the values that we obtain there, right? So it's these values minus the corresponding mean. These values minus the corresponding mean there. Then what is the next part? The next part is we want to find the product of this column and this column. So that's what we need there. We need the product. You can see the formula there needs the product. So we find the product. This is easy. Negative 3 times negative 20. So we want to find the product. Negative 3 times negative 21. You don't even need a scientific calculator. You can do it mentally. And that is 63. Right? And the same there. Negative 2 times negative 12. Negative 1 times 1. Negative, it's not negative 0, it's just 0. So that is 63 and then 22. And there's all the product of that. 0 times negative 3 is 0. Okay. And what's the last part of the formula there? We need to find this first column and it needs to be squared. Negative 3 squared is, so that's what we need to do. That should be easy. That is 9, that's 4, and that's 1, and that's 0, and that's 1, and that's 4, and that is 9. So we can calculate all these squares there. So there we've worked out those. What does a sigma mean? That means a sum. So we have to sum this product, and we need to sum the square. So we have to sum this there and sum. So we find the sum. You can either do it mentally or you can just use your calculator. So the sum of that column, of this particular column here, is 168, and the sum of this column here is going to be 28, right? Let's take the others away. So because this formula needs the product, you can see it needs the product and it needs the square. So we only need those two. Let's take the other columns away there. Okay, so let's try calculate the b value and the a value and then write down the line equation for the line of best fit. Now let's find the equation of the line of best fit using the values that you obtained from the tables. Let's just get the values back again. That was our data set that was given, and that was the mean for the x values, and there we have the mean for the y values, and those were the two columns that we calculated, the product and the square. And then we found the sum, which is 168, and the sum for the squares there is 28. Right, let's get our formulas back. That's a predicted value. Equation for the predicted value, y hat is equal to a plus bx, and that's the formula for the b. Okay, so let's see. For the numerator, I need the sum of the product, which is 168, and for the denominator, I need the sum of the squares. So that's correct. It's 168 over 28. That's quite an easy calculation. It goes in there exactly 6. Okay. Then to work out the A, we're going to use this formula here. I have to substitute the mean for the Y values, which in this case is 70, minus the B is 6. 6 times 4, and if we subtract that there, we get 46. Now it's just a matter of putting it in. So there I get Y hat is equal to 46 plus 6x, where 46 represents the Y-intercept and 6 is the gradient. And there we found the equation of the line of best fit for this particular data set there. Now here's an example for you to try, right? So I've just put down a template just to make it easy. We're going to have 4 x values with corresponding 4 y values. Let's try to do that. Give you a chance to fill in the columns. That is the product. So we'll put in here, we'll put in the for the difference of the x there, we'll fill it in this column. For the difference of the y in this column, then the product, you'll put it in there. Here you'll square this column and enter there. Do the necessary calculations. So I suggest you pause the video and then we'll look at your solutions there. So let's pause. Now let's just look at your answers there and see what we've done there. So there's the template that we had there. So we've got the mean. You've corrected the mean is 5 and the mean for the y is 60. So if that's correct, you've worked out that correctly. Now we need to complete the columns, and you can see the difference of the x there. 2 minus 5 is negative 3, etc. And then 50 minus 60 is negative 10. Then we have to find the product. That's 30. See, it's easy numbers. I didn't take any decimals there for you just to understand your formula. And square that. You don't need a calculator. That's 9, 1 and 1 and 9. And now we just need to find the sum of the product. And the sum of the product there is 180. And we need to find the sum of the squares. You can even see there it's exactly 20. It's quite easy. Now we substitute. So there we need the sum of the product over the sum of the squares, which is 180 over 20, which is quite easy. That is 9. So now we need to substitute to work out the A. It's going to be the 60 minus 9 times 5. So that's 60 minus 9 times 5. And that is going to be exactly 15. And now we can get the equation for the predicted value. So y hat is going to be 15 plus 9x. Easy, right? I've just taken this example without any decimals for you to get that. Just a very cosmetic, but it can give you practice of how to apply using a table using the formula and then using a table to get the values there. Right? Especially if you don't have a scientific calculator, this is the way in which you can calculate the equation for the line of best fit. Now we're going to look at the easier option of finding the equation of the line of best fit, and that is using your scientific calculator but using the stat mode. So let's assume your calculator is on, and you see you find that particular key on your calculator. You enter that, just press the mode setup key, and if you do that, you'll see that on your screen, right? And then because we want the stat mode, you choose, you can see the stat mode. There's the stat mode 2. So you enter 2, and when you do that, you'll see that popping up on the screen. We want the equation of the line of best fit. Can you see which number we have to choose? That's right, that's the one we want. So you enter 2, and when you enter 2, you'll see that is the line of best fit equation that we want. If you enter 2, you'll see there's a table. So you have to put the independent values, variable values in there, and the dependent variables. So that's the x values. It's always, maybe just enter the x values first and then the y values, right? And how do you do that? You press 1 and then an equal, so it saves it there. And if you do all of them, that is what you'll see on your screen there. And you can actually scroll down if you want to see the other values. So it's 1 and 49, 2. So you press 1 equal, 2 equal, 3 equal, etc. Right? So I've just made nice cosmetic numbers for you to practice. 1, 2, 3, 4, 5, 6, 7, etc. And then these are the corresponding y values. So this is just if you want to scroll. If you made a mistake, you can go scroll up or scroll down. You can go scroll left or scroll on the right side. So once you have done that, you must save those values. And how do we save that? You go to there's a key there, the AC. You see the AC there? Press AC, so now it is saved. And don't worry if you see now the screen is blank, right? Because it's saved. But how can you now, to get the values now, you press shift. You see the shift key, and then immediately after the shift key you press, there's a stat key, stat 1. And if you do that, this is what you'll see on your screen. What do we want to do? We're busy with regression, so that is number 7. So you enter 7. It depends on your calculator. Some calculators you have to, it will be 5. You press 5. So it just depends on your model of the calculator that you have. So if you do that, you'll see this appearing on there. So there we've got the A value, which is the Y-intercept, and the B is the slope, and R will stand for, that's right, correlation, right? And let's leave out the other. We're not going to use the others there. So I want to find the A and the B value. So that's what I just want to find the A and the B. So if I press 1, right, you'll see that will be the value that will appear on your screen. If you press, then you go back again, maybe shift and stat, choose regression again, and then you get B, and B will be 6. And now you can write down the equation of the line of best fit, which in this case is the same as the one that we used with the table method, 46 plus 6x. You can just verify this is exactly the same values, and the calculator will give you exactly the same values there. Okay, now let's see whether you can use your calculator. I'm just giving you another one. Remember this one that we have there? Maybe you can't remember the answers. Just see whether you can follow all those procedures. Shouldn't take you longer than 2 minutes. So let's pause the video, try it, and then we're going to look at your solutions. Okay. And see, there's the template that you can use. You must find a B value and an A value. Then you write down your equation for the line of best fit. Give it a chance. Let's see there. So that's what we want. So if you use your calculator, you'll see B will be 9. Did you get that? And you'll see A value is 15. And there we've got exactly the same equation. Y hat is equal to 15 plus 9x. Okay. Hope this helps you. So you have the option there. If you don't have a scientific calculator, then you'll have to use the formula with the table, which is much longer. But most of you have scientific calculators, so you can do it on the scientific. There are other techniques also, which is using Excel, etc. But you can't use a computer in the exam. So it's either using your scientific calculator stat mode, or if you don't have a scientific calculator with a stat mode, then you'll have to use the formula with a table. Now in this section here, we're going to look at trend, outliers, prediction, and correlation coefficient with some explanation and some examples. One of the things that you need to be able to do is to determine the trend of a relationship. So a trend is a description of the relationship between the independent variable and the dependent variable of the data set. Then it's also clearly the trend should be, description should be of such a nature that you can clearly see what the direction of the regression line or the line of best fit would be. Let's consider this particular example here. 12 athletes trained for the 100-meter sprint event. The number of days training in seconds to run the distance are shown in the table and in the scatter plot below, right? So after you have got the table, you've got the scatter plot. Now the question is, discuss the possible trend of the data. So the trend, it should be the relationship between the independent and the dependent. So if I look at the independent, as the number of days of training increase, what is happening with the time? You can see it's a negative slope there, is decreasing. So let's write that down. As the number of days that an athlete trains increased, the time taken to run the 100-meter sprint decreased. So there we've got increase and decrease. We can also write it differently. If we look at the the fewer number of days that an athlete trained, the fewer or number he trained, you can see then it's less than the longer the time taken to run the 100-meter sprint. Right, so any variation of that, and let's put the other one back again. You can see those are two possible options there. Now let's look at the concept of outliers. Suppose there is an observation in a data set that has a very high or very low value as compared to the other observations, then such an observation is called an outlier. Okay. Now, outliers are data points that are numerically distant from the rest of the data set. Right? So you'd see that it doesn't compare with the other observations. Let's look at some outliers here. As you can see there, we have a data set and we've got 4 points A, B, C, and D. And you see it's far from there's the cluster of points there, and the A seems to be away from the cluster, B seems to be away, and the C and the D. So let's look at each one. Now, if we look at outliers here, we can look at in the direction of the X. Okay, so we're going to look at A, B, C, and D. Now, if I look into that X direction, you see there's the range for the X, so that's the from that point, which is about 0.2, and that's about 4 up to 4.3. So that's the cluster is between 0.3 and let's say 4.3. So which points with regard to the X is outside the screen? The A is not outside. You see A is within that green, D is within the green, B is outside, and C is outside. So let's do that. So in the X direction, it will be B and C. If we consider the Y again, see that's the range for the Y. So if I look at the Y, you see C is within the Y. A is outside the Y. See, it's outside that. And the B is also outside, the D is in. So this is going to be A and B. So you can see B in this case is both outside the X direction and outside the Y direction there. And if I look at D, D is within. You see D is within there. Now D is also an outlier, but in this case here, when it's within that range there, then we would say that D is a bivariate outlier. Okay. Now let's look at the influence of outliers in the X direction and the Y direction. Okay. So if we take this data set, and there is the regression line, which is in this light blue magenta color, and I'm taking this particular point, this point here, you can see it is outside in the X direction. So that point C, now if I include the point C and I recalculate the regression line, I get a new regression line. And you can see this regression line seems to be, doesn't fit in with the regression line without the outlier. Let's take the other situation where I take my data set and I add a outlier that is now outside in the Y direction. See, in the Y direction it's outside. That's also an outlier. But when I calculate if I just add that point now in with this data set here, it seems to be not far out from the original one. So what can we deduce from that? In the X direction, if it's an outlier in the X direction, then it greatly influences that, right? And if it's an outlier in the Y direction, it doesn't. So whether you include it or not is not going to make a difference, right? But if you include it in the X, if you include this point here in the X direction, okay, then it's going to greatly influence the line. So then you can decide whether you want to include the outlier in your calculation or not, right? But you can see the implication if you include an outlier in the X direction. Now let's look at an example here. Here we've got 12 athletes that are trained for the 100-meter sprint event, and the number of days training and the time in seconds to run the are shown in the table below. So the number of days and the time is shown in the table and in the scatter plot. So now we're asking you, identify the outlier. Now if you look at that, you can see there's an outlier. And what's the corresponding point? 60 and 18,1. So there's your outlier there, right? So there we've identified that outlier. You can see there, it's outside this. Yeah, it's a way, if you're going to have the regression line there, all these points are clustered close to the regression line, but that one seems to be out there. Maybe a possible explanation. This is a person who trained for 60 and he is really not doing well. Maybe a possible reason is just his off day, or he was maybe injured, so he's underperforming there compared to the others there. So there could be many reasons you could use. Let's look at prediction in a little bit more detail here. Let's consider this case here. We've got duration of study in hours, and we've got the exam result in percentage. There's the data set, and that is the line of best fit. So if we look at the range of the data, the range of the independent variable, right? So if we look at that, that's the range of the independent variable, right? So interpolation is if you make a prediction inside the range of data. So any prediction that you make from that point to that point, that will be interpolation. Okay? But if you take a reading here outside that range, in other words there, then that is known as extrapolation, right? That's outside, so that will be extrapolation. So any reading you take here, that will be an extrapolation. Now with extrapolation, sometimes it is best to avoid extrapolation. And just to give you an example here, if I take the same example, I've got the duration of study in hours, and then I have the dependent one, exam result in percentage, right? So what is extrapolation? Making a prediction outside. So let's just take an example. Let's say, so there's the interpolation. Any reading there, that will be the interpolation. That's my range of my data here. So let's say 14 hours of study. Right, so let's get 14 hours. There's 14 hours. I go to my line of best fit and I make the reading there. And if you just approximate that, what do we think it is? Let's say it's 115%. We could also have used our line of best fit equation and substitute 14 in that. Let's do that. So I take 14, substitute, I get 111,4%. But what can you tell me about this? 114%. That's not possible. Why? Because the maximum you can get is 100%. You see? So in extrapolate, in this case here, doesn't fit the real life situation, though. That is unrealistic. Now let's look at an example here. We take the same example. This is again the 12 athletes, number of days that they've trained, and the time taken to run the 100 meters sprint. So there we've got a table, and we also have the scatter plot. Let's look at the question here. Predict the time taken by an athlete who trained 45 days. So what do we need? We need the equation for the line of best fit, right? So there's the equation of the line of best fit. Let's say it was, you calculated it, so you use that. 45 days. Days is the independent variable, so that's the x. So I substitute. So I have 45 in place of the x, and I compute that. I get 14,6. So to do a prediction, you just substitute into the line of best fit. And you can see that 45 is within the range of the data, right? So that is interpolation that I'm doing there. If you recall, we said the correlation, measure the strength of the relationship between the independent and the dependent variable. And we know correlation is a value between -1 and 1. And just we had this previously, just to remind you, We have perfect correlation, we have no correlation, we have weak, and we have strong, and we have moderate. And with strong, maybe you can have two very strong and then strong within that range, and the same applies to negative, right? So we can calculate the value of the correlation coefficient using stat mode, right? So that is what we're going to do. There is actually a way to calculate it without using the calculator, but then you have to use a very complicated formula. There's the formula, and this particular formula is not CAPS compliant. That is the South African mathematics school syllabus for grade 12, right? Where you can see this is a familiar part of the formula there. There we have standard deviation. We're not going to bother doing that. You just use your calculator to get the correlation coefficient. Okay, so let's take an example now. We take our same example of our 12 athletes, and we want to calculate and comment on the correlation coefficient. So using the calculator, that is the correlation coefficient. You can see from the graph even that this is a negative correlation, right? The trend, there's a negative trend, so it's negative. But let's comment on that. So first of all, we can say it's negative. Now, is it weak or strong or very strong or perfect? It's definitely not perfect, and it's not very strong, so we'll just say it is a strong. You see, it's within that range, right? Negative 7,4 is between negative 0,6 and negative 0,1 from what we had from our table. And then, so we can just say it's a strong negative relationship between the variables. Okay. And now we're going to look at our application. Let's take the example here. The table below represents the dates in June, the month of June, and corresponding number of patients who were treated at a local medical facility on those dates. So there I've got, as you can see, there are 8 dates here. And then we have the corresponding number of patients who visited that facility there. So on 3rd of June, there were 270 patients. On the 19th of June, there were 650, etc. So we want to find the relationship between the dates in June and the number of patients who visited, were treated at that medical facility. Not just visit, they were treated there. So in this particular question, we want to represent the data in a scatter plot. That's the first question. Then we want to write down the trend, right? And then we want to find the equation of the line of best fit. And then we want to calculate and interpret the correlation coefficient. We want to predict the number of patients on the 30th of June. And then I want you to draw the least squares regression line, or the line of best fit, on that scatter plot. And then this is a typical examination type of questions. I'm just including all of them. You won't be assessed on all of them. And then we want to comment on a particular point and provide some interpretation there. So in the next slide, we're going to do the detailed solution to each one of these questions here. Now let's look at the solution to this. I'm just putting in the data set up there for easy reference. We want to represent it on a scatter plot. So you know, with the scatter plot, you will need your axes, and seeing this, you normally provide it with a grid there. So on the horizontal, we want the dates in June. So I need the dates in June. There's 30 days, so you go up to 30 days in June, not 31, not 100. And then we look at the number of patients, and we see that we've got 825. So let's go up to 900, right? And then we just label it days in June and the number of patients. We need a grid. So we want to plot 3 and 70. So there's 3 and 70. Then we want to plot all the points, and there's all the points plot. So you should know how to plot the points there, right? So there we have our data set represented in a scatter plot. Let's look at the next question. Now we want to discuss the trend. Now the trend here is the relationship between the independent and the dependent variable. As you can see here, it is a positive correlation. So we can say as the days increase in June, the number of patients treated also, you can see it also increased, right? So that's the trend there. Equation of the least square regression line. Yeah, I assume that you're using your calculator. So that's the equation. So the A value from the calculator you should get is 158,31. Not going to go through the process of using your calculator here. And then the B value there is 26,58. Now we write down y hat is equal to 158,31 plus 26,58. I color coded for you for easy reference. Calculate and interpret the correlation coefficient. So also from the calculator, you go to the regression, which is either number 5 or number 7 on your calculator, and the value we get there is 0,99. But the question says interpret. So what does that mean? 0,99 is very close to a perfect, right? So we can either say it's a very strong positive correlation. Only be perfect if it was exactly 1, and it's not exact. It's a very, very strong positive correlation. Predict the number of patients. So we have to use our line of best fit equation, but in this case 30th of June, so I put in the 30 there, and then if we calculate that we get 955,71, and as you know, you can't get a fraction of a patient, so we're going to write that as, that's correct, 956 patients there. Okay. Now let's look at the next question. Now I want to draw the least square regression line. So we need the equation, but to be able to draw any straight line you need 2 points. Now plot 2 other points that are not plotted there yet. We want the y-intercept, so let's work out the y-intercept, which is x is equal to 0, so the y-intercept there will be 0 and 158. Let's plot that point. There's the point that we've plotted there. Then next we want, there's the point, we've plotted the point 0, 158, and then we want to find another point. You can choose any other point. Let's choose 10. That's some nice points there, 10. And if you calculate that, that's going to be 10 and 424. So we plot, there's the 10 and the 424. So let's put the point in there. There's the 10 and 424. Now we can draw the line. So you just join those 2 points, and there is your line of best fit. Okay. Now we want to comment on the point 1600. Let's find 16. That's 16th of June, and 100, which is somewhere there. There's the point. Now what do you notice about that point? That's correct. It's an outlier. Okay. But now they say provide some interpretation. You're South African, so you should know what's the significance of the 16th of June. 16th of June is it's Youth Day. It's a public holiday. So maybe on that particular day, not so many people went to visit the hospital. They're either going to the beach or attending a function. So it's an outlier, and a possible explanation is because it was a public holiday, few patients were treated or visited the facility. And that's the solution to that particular example. Now let's look at the most important part of the video, and this is the exercise worksheet for you to do. This first question here has been slightly adapted from the November 2014 DBAE paper. As you can see there, we have going to find the relationship between mathematics and accounting, and that's the percentage, and you're provided with a scatter plot, and there are 3 questions that you have to answer, right? So give you a chance. The solutions to this will be provided in another video, and then now the second question here is adapted from the November 2015 paper, and there's a table that shows a relationship between the total fat and the energy of 10 items, and in this particular one you have to draw the scatter plot, find the equation of the least squares regression line, which is the same as the line of best fit, and then we might need to predict the number of kilojoules of energy for a specific item, and then I want to show you how to draw the least squares regression line, And then lastly, we need to calculate and interpret the correlation coefficient. And then I have one other question. This is one adapted from the June 2017 DBE paper. And this is the relationship between time taken to develop an app and the cost per 1,000 rand for the app there. And in this question here, we just want to determine the equation of the line of best fit, and then we want to make a prediction, and then we want to calculate the correlation coefficient, and then there's an additional question that you have to answer there, right? The solutions to these three questions, I've uploaded the solutions in another short video, so just to give you a chance to try it on your own first, and the detailed solutions you'll find in another video. I hope you benefited from this video and you have a better understanding of the topic of the line of best fit, and specifically the concepts of correlation and regression. Please subscribe to our channel so you can always get the latest videos, and solutions to all exercises of all other videos, mathematics videos, are also available and has been uploaded.